Greetings, everyone. My name is Yongxin Zhao. I'm here to share our work on when large language models listen to experts, accurate failure diagnosis in operating systems. This is a joint work of researchers from Nankai University and Tsinghua University in collaboration with Alibaba Group. In this presentation, I will walk you through the motivation behind our work, the design of our approach, and the key results we achieved. Operating system failures in cloud environments are both frequent and costly. Even a single failure can quickly propagate across services, leading to system-wide disruptions. Now, let's look at how diagnosis is done today. After an alert, engineers manually collect multimodal data, extract abnormal signals, and search for similar historical cases. They then rely on troubleshooting guides and standard operating procedures to infer the root cause. However, this process has clear limitations. It's manual, time-consuming, and error-prone. An internal investigation at Alibaba shows that the average time to diagnosis is around 2 hours, while complex cases may take several days to resolve. Therefore, efficient failure diagnosis is critical for ensuring system reliability in production. However, existing automated approaches are often black boxes, lacking transparency and interpretability, which limits their practical adoption. Recently, large language models open up new opportunities for failure diagnosis, thanks to their strong reasoning and semantic understanding capabilities. However, applying large language models in this domain is still challenging. First, they lack structured troubleshooting knowledge. In practice, troubleshooting guides are heterogeneous and inconsistently written, making it difficult to retrieve and reuse relevant knowledge. Second, their outputs are often unreliable and non-actionable due to limited domain-specific training. Third, the interaction between engineers and large language models is still limited. Engineers often need clarification, but current systems don't support effective iterative interaction. To address these challenges, we propose OScope, a practical large language model-based framework for operating system failure diagnosis. First, to overcome the lack of troubleshooting knowledge, we fine-tune large language models on a domain-specific data and align anomalous features with historical failure cases, enabling accurate retrieval of relevant troubleshooting gaps. Second, to improve actionability, we introduce SOP-based templates to structure diagnostic reports and further refine them with retrieved procedures to ensure reliable and actionable recommendations. Third, to enhance human-AI collaboration, we design a human-in-the-loop mechanism that supports interactive refinement, allowing engineers to iteratively improve diagnostic results. Now that we have discussed the challenges, I will move on to the methodology and introduce the design of our approach. OScope is a novel large language model augmented failure diagnosis framework. As shown in this figure, OScope consists of 3 key modules: data analysis with knowledge retrieval, SOP-guided failure diagnosis, and on-call engineers large language model in the loop. This slide presents the first component of OScope, the knowledge aligner. Its goal is to address the lack of structured troubleshooting knowledge, especially the inconsistent and ambiguous symptom descriptions in historical cases. The key idea is to standardize unstructured symptom narratives into structured representations that align with operational semantics. When a failure occurs, OScope collects multimodal data, such as metrics, logs, and stack traces, and extracts anomalous features. These features are then summarized by the knowledge aligner into a unified semantic presentation, which is encoded as a query. Finally, this query is used to retrieve similar historical cases, enabling accurate and knowledge-driven diagnosis. Built on the knowledge aligner, we now move to the second component. This module addresses the issue of unreliable and non-actionable large language model outputs, which often result from insufficient procedure knowledge. The key idea is to explicitly guide diagnosis using standard operating procedures. Specifically, the diagnosis analyst first generates an initial diagnostic report by combining anomalous features with retrieved historical cases and structuring the output with predefined SOP templates. Then, the report validator further refines the report by aligning it with relevant SOP documents, ensuring that the final diagnosis is both accurate and operationally actionable. We finally introduce the third component, an interactive human-in-the-loop mechanism. This module aimed to bridge the explainability gap between engineers and large language models. Specifically, the system improved transparency by attaching confidence scores and traceable evidence to each diagnostic conclusion. At the same time, it enables interactive refinement, allowing engineers to request clarifications or drill down into specific reasoning steps. To illustrate this, let me walk through a real case. An engineer observes abnormal disk utilization on a machine and submits the request to OScope. The system collects multimodal data and detects anomalies in memory-related metrics and stack traces. The knowledge aligner then structures these signals and retrieves relevant historical cases. Based on this, the diagnosis analyst generates an initial report following SOP templates, which is further validated by the report validator. However, the engineer notices that memory usage is still below the threshold. Through interaction, the system reanalyzes the signals and highlights an abnormal increase in memory recovery time. This leads the engineer to identify the actual root cause, a memory leak. Next, I will present the evaluation results to demonstrate the effectiveness of our approach. We evaluate OScope from three aspects: effectiveness, component contribution, and practical usability. First, in terms of effectiveness, OScope significantly outperforms the baseline methods in diagnosis accuracy. Second, the ablation study shows that each component is essential. Removing any module leads to clear performance degradation. Third, from a usability perspective, user studies confirm that OScope generates clear and actionable reports, which are highly valuable for engineers in practice. This figure demonstrates the effect of semantic alignment in the knowledge aligner. Here we show a representative failure case with 2 human written symptom descriptions and 1 system detected anomaly. These descriptions differ significantly in terminology and style. After applying the knowledge aligner, they are transformed into consistent semantic representations. As a result, the pairwise similarity between them is significantly improved, which directly enhances the reliability of knowledge retrieval and case matching. Next, this figure illustrates the effect of SOP-guided validation in our second module. We compare the original diagnostic report with the validated version. Here, red text indicates corrected errors, while orange text shows additional complementary information. As we can see, the validation process not only fixes incorrect conclusions, but also enriches the report with missing details. More importantly, it ensures that the identified root cause is accurate and that the recommended solutions are adapted to the specific operating system version, making them truly actionable. Finally, I will conclude the presentation and summarize the key takeaways of our work. To summarize, we propose OScope, a novel framework that integrates semantic alignment of expert knowledge, SOP-guided reasoning, and human-in-the-loop collaboration to enable effective failure diagnosis. In terms of performance, OScope achieves state-of-the-art results, reaching 90.1% top 5 accuracy on a real-world operating system failure dataset from Alibaba, significantly outperforming existing baselines. More importantly, OScope has demonstrated strong practical value in industrial settings. It has been successfully deployed in production, reducing the average diagnosis time from 112 minutes to just 1.5 minutes, and helping resolve 67 critical failures. Thanks for listening. If you have any other questions, feel free to contact us via the email at the bottom.